Hey everyone. So here's the optional black hole lecture that I think, just to make it kind of self-contained, is going to be more or less what we talked about in class plus extra stuff. So I'll put timestamps in the caption for this video, so if you want to jump around, you can. But anyway, we'll essentially start from the beginning, which is why this video is as long as it is. So if you want to jump around, jump around. Else, you can review and watch it from scratch. So this was motivated, our idea of black holes was motivated by us talking about the deaths of stars, how things like our sun and how things that are more massive than our sun and less massive than the sun eventually will reach the end of their lives. They are all starting right now as main sequence stars, where they are fusing hydrogen to helium in the center, and the rest of the stars just kind of hanging out, being hot and glowing. Once stars run out of hydrogen in that hot, dense core, whether or not they are super large stars or very low mass stars, they will divert on two different paths. Stars like our sun, or things that we think are less than about 8 times the mass of the sun, go through the stages of they become a big old red giant. That big red giant then fuses helium into carbon and oxygen in the center of the star. All the while, its outer layers are being kind of burped off, which we call the planetary nebula stage. That reveals ultimately a very dense, hot, compact object in the center of mostly carbon and oxygen that used to be the center of the star, but now is just a bunch of inert, very hot leftovers. We call that a white dwarf. The white dwarf is held up against gravity by electron degeneracy pressure. It's the actual electrons that are holding up, stopping gravity by this weird quantum mechanical thing that's going on. But again, it's that they're being held up by electrons not wanting to be crammed too close to one another. And the electrons can only work so hard, and once you get above about 1.4 times the mass of the sun, the white dwarf itself explodes. In contrast, for the more massive stars, they again become what we call red supergiants instead, where they start fusing helium to carbon and oxygen in their cores. But then they keep going, and from that helium, they make the carbon and oxygen. From the carbon and oxygen, they make silicon, and they keep going all the way up the periodic table to about iron and nickel. At that point, they can't go beyond iron and nickel because it turns out that the nuclear reaction becomes endothermic versus exothermic, so it doesn't naturally occur in the center of the star, because the star is doing this because it's trying to release energy to keep it hot, to keep itself supported against gravity, who never has stopped trying to pull things together. Eventually, though, the core gets way too big, and the electrons, again, can't really stop gravity from doing its thing, and the entire core implodes, which causes a type 2 supernova. What's going on in the core then is that all of the protons and electrons are essentially crammed on top of one another. They then turn into neutrons, and as a result, you get a neutron star at the end of the day. And we think that then the neutron star cannot be arbitrarily massive. It can only be about 3 times the mass of the sun before even the neutrons give up against gravity. And then nothing can stop gravity, if you're above 3 times or so the mass of the sun, once you get to this leftover stage. Of course, it started with much more mass, right? We could have 30 times the mass of the sun. A lot of it gets lost along the way and kind of gets thrown off or burped off or thrown away during the supernova, so that the part that's left over is, at least to date, we've never found anything bigger than about 3 times the mass of the sun, because we think that's about where the neutrons even give up. Just how we have not really ever seen a white dwarf more than about 1.4 times the mass of the sun, because that's when we think the electrons give up. And these are super, super dense objects. Again, this is the idea. If you were to take the entire sun and cram it down to the size of the Earth, that'd be roughly the density of a white dwarf. Where then if you took the entire sun and crammed it down to about the size of San Francisco, that would be roughly the density of a neutron star. Very, very dense, compact objects that just cash in on their life savings. So we sometimes call them retired stars. They used to be the hot centers of cores of the stars. They are no longer producing any new nuclear fusion, so they just gradually cool off for the rest of time. And with these super, super dense objects, we then had to consider things like how does gravity behave around these very dense objects? As we walk around on Earth, gravity is pulling us towards the center of the Earth, and with not a unreasonable amount of pull, right? If I jump into the air, I can't obviously escape the Earth, but I'm not feeling myself crushed down against the surface of the Earth. And that's just because the mass of the Earth is not that large, at least compared to, say, if I tried to walk around on the surface of a white dwarf. Then I have essentially the entire sun trying to pull down on me, over very, very small distances. And then that gets into our discussion of Newton's gravitational equation, gmm over d squared. The d becomes very, very small in these cases for a very, very large amount of mass. So you get big gravitational forces. And then this becomes even more extreme around neutron stars. And so that's where we enter the realm of Einstein's general theory of relativity, that you need to consider what gravity is and how it operates on a more sophisticated view compared to what we talked about with Isaac Newton, where in terms of general relativity, Einstein was able to describe that gravity is a distortion of space-time itself as a result of mass and energy. That if you just have mass, or even in this case, he upgraded it to even if you just have pure energy, like light, you can distort space and time around that region, which then dictates how things might move in the general vicinity of those objects. So we have the example of if I were to throw a marble across a table, it would travel in a straight line. That's the idea of kind of flat space. Space is not distorted in any way. So the marble wants to travel in a straight line because there's nothing dictating to the marble that it should do any different. Straight lines are kind of the default unless there are forces or reactions that require it to take some different path. Then if I take this table, or consider a big piece of cloth, and put some sort of massive object in it, that distorts the shape of the fabric or the shape of the table. And so then this marble, if I'm trying to throw it along in a straight line, it doesn't travel in a straight line, but as a result curves around because of this distortion in space itself. And that's the basic idea of general relativity. It's just a distortion in space itself that is causing these deflections. Gravity is a geometric reaction or force, or rather, gravity is a geometric result, not actually a force if you think about it in this way. The red ball follows its natural path in this kind of curved space. So here's kind of a fun animation. You can imagine this being the sun, and then this being, say, the Earth. As the Earth goes around the sun, the Earth is constantly kind of falling into the cavity that the sun is creating by it being weighting down the cloth. But since Earth has that kind of tangential or sideways velocity, it always, as a result, falls around the sun rather than falling directly into the sun. If the Earth, if I would just release a marble from rest on the cloth, obviously it would fall directly towards the center. But since the Earth kind of already has this kick over to the side, it falls around the sun rather than falling into the sun. And then you can see that even around the Earth has its own little relative distortion, where maybe if you had a little moon, a moon could then kind of orbit around the Earth as the Earth itself kind of went around the sun. So it's all geometric effects. So then we can upgrade our ideas on thinking about what happens beyond things like the neutron star. These neutron stars, again, very dense, very compact, strong gravitational forces, but the neutrons are preventing the neutron star from getting any more dense and compact, so it can stay as some sort of physical shape. If instead it were to become larger than we think about, roughly 3 times the mass of the sun, then even the neutrons give up, and the entire neutron star collapses in on itself as a result. And at this point, we'd have no idea in physics of what could possibly stop all that stuff from just collapsing in on itself denser and denser and denser and denser. Nothing stops it from collapsing, maybe perhaps literally to a point, or something that's incredibly small in volume. There's this idea we have called quark degeneracy pressure, where it might be the quarks are things where if you take a proton or a neutron and you cut it open and look inside, neutrons and protons actually are made up of tiny little individual constituents called quarks. So we think that maybe something like that could hold up whatever the neutron star ends up collapsing down to become. However, it's almost a moot question because it's something that we can really never actually study, because the thing becomes what we call a black hole long before it even reaches that point. And whatever is going on inside the black hole, it's impossible for us to study. Because these are things where not even light, the thing that travels the fastest in the universe, right? Nothing can go faster than the speed of light, where not even light can escape. Nothing is reflected, nothing is emitted, at least from the object itself. It is purely black. These are exciting objects because we think that very, very massive stars might collapse into these things where it just skips the neutron star entirely. Or if you have two neutron stars that run together, or a bunch of things that kind of cram together, maybe you can form a black hole just by getting, again, enough stuff in a small enough space that nothing can stop gravity from causing it to collapse down to a singularity. And around that singularity is then a region where not even light can get out. So it doesn't even matter kind of what's going on in the center. There's enough stuff inside that gravity stops anything from getting out. Once inside, always inside. And of course, these are fun, exciting objects, right? You know, if you've heard of anything in this course, you've probably heard of black holes, but maybe haven't really learned anything about them. You know, they show up in popular culture all the time. You know, if you include the term black hole in the title, it usually sucks people in, so to speak. Right, so you got Disney's The Black Hole, Event Horizon, Infinite Space, Infinite Terror. I'm pretty sure this movie actually has nothing to do with black holes. Just like how this is a graphic novel, I think that's about zombies. It's pretty good, though, I'm told. That's a pretty good graphic novel. But these are exciting things, right? You can look just as Google image searches. If I just Google or not even image searches, Google search black hole, 3 billion results in half a second. Really, in half a second. I still don't fully understand how the internet works. But 3 billion results by just typing in black hole. And the first couple hits are usually pretty good, especially now, like one of these images are showing, we've actually been able to directly observe these black holes, which is a first, right, in the last couple of years or so. And even in comparison to last year, here's the slide I showed in last year's version of this class, only 1.7 billion results in 3/4 of a second. So over the course of 1 year, it's almost doubled in the number of results and hits out there of people thinking about black holes. Very exciting topic, and actually not that hard to understand, at least at the basic level. A lot of the understanding of black holes you can actually understand without needing Einstein's general theory of relativity. You get more or less the right answer if you think of this in terms of purely Newtonian mechanics. So the idea is that this is a region of space where not even light can escape, let alone objects that have mass like you or me, or apples that might be thrown into a black hole. And so the idea is the idea of an escape velocity, if we want to think classically for a second. Right? I have this apple, and I can throw it up into the air, and if I throw it with a little bit of oomph, it goes up into the sky and then falls back down pretty quickly right away. You can imagine if I throw it with a little bit more speed, it gets higher and higher, but eventually falls back down. If I didn't have a ceiling above me, I could even try to throw it higher. And the faster I threw this apple, it would sail up, slow down, but eventually reach my hands again. The apple cannot escape the earth because I'm not throwing it fast enough. You might imagine there's a point, right? Again, if I went to the gym more often and I didn't have a ceiling in the way, that I could throw this apple so fast that it would get farther and farther away from the earth. It would always be slowing down because Earth's gravity would be trying to pull it back, but it would never actually turn around and come back. It would escape. We can define this as something called the escape velocity of an object. And it's not too hard to derive, actually. This is usually a problem that we do in groups in my Physics 1 course. But you can derive for an object that has a given mass, where you're throwing it from the radius of the object, an escape velocity, how fast you need to throw the object so that when I throw it into the air, it does not come back. And it involves, right, Newton's constant g and square root of 2gm over r. If you plug in the mass of the Earth and the radius of the Earth, so that'd be how fast you have to be moving to escape from the surface of the Earth, it's about 7 miles per second, or about 25,000 miles per hour. So rockets need to be getting up to speeds comparable to this speed if they have any hope of making it off the surface of the Earth and not falling back down if they want to, say, go to the moon or go to Mars. So that's the idea of the escape velocity. And you notice, since the mass is in the numerator, the more and more massive it is, the larger the escape velocity is. It takes more speed. Oops, I lose my apple. It takes a larger speed to get off a more massive object. Or if I made the object smaller and more compact, so I took all that mass and put it into a smaller and smaller volume, this escape velocity also increases as a result. And you can imagine, right, if it's 25,000 miles for the Earth, it's even larger for the Sun. You can imagine getting the mass so big or the radius so small that this escape velocity starts to become comparable or even exceeding the speed of light. And since nothing we think can move faster than the speed of light, and light itself is the fastest thing out there and it moves exactly at the speed of light, then that suggests that not even light could possibly escape from something where the escape velocity exceeds the speed of light. And again, for the Earth, it is far from being equal or comparable to the speed of light. And so this is the idea, kind of classically, of how you can think about a black hole, right? If we bring in relativity, right, the idea of the sun kind of distorts space around it, so marbles kind of fall in towards the center or fall around the sun. Neutron stars have about the same amount of mass, but a smaller volume. So they create a more significant distortion, at least while you're nearby the neutron star. So things that are nearby will really feel themselves falling in. Or light that is trying to escape from the neutron star has to climb out of this big well before it can escape back out into space. And when we talked about general relativity, remember we said one of the things that relativity showed us is that light loses energy as it tries to escape from an object. I shine a flashlight into the air. As those photons try to make their way out into space, they actually lose a tiny little bit of energy along the way. Just like the idea of how you lose energy when you try to run up a hill. You might be going really fast at first, but as you run up the hill, you slow down, right? You get tired out. Same thing with light. And so then the black hole is the extreme limit of this, where it turns out you can work out mathematically, the length of this well essentially becomes infinite in length, and it becomes so steep that it's kind of like trying to climb out of a greased well. It becomes impossible for anything with mass, and anything with photons, even as they're trying to climb up this exceptionally steep well, essentially lose all of their energy in the process. So before they make it out, quote unquote, of the black hole, they lose all their energy and as a result cease to exist. So light doesn't get out because it's more or less destroyed along the way, and then its energy falls back into and is just always part of the black hole. So I think Dante's quote is apt here of just abandon all hope, ye who enter here, because once you find yourself within a black hole, right, you find yourself in that greased well, you're not going to be able to escape. Even if you're light, even if you have a rocket booster that can get you even close to the speed of light, you don't have enough energy. It would require an infinite amount of energy if you would have any hope of escaping from the black hole itself. So they draw you in, black holes draw you in and hold on fiercely once you get too close to the black hole. So how close is too close? Right, maybe, I require that Kaylin and Justin, our TAs, where I have to go study a black hole, else I'm not going to let them graduate. If they want to get close to a black hole, they can't get too close to a black hole because else they're never coming back. So where is a safe distance? Where's the region where I could safely hang out around a black hole without having to worry about getting sucked in, so to speak? So this actually you can derive pretty easily. There's something we call the event horizon, which is the location where if you're closer to the black hole than the event horizon, it's game over, right? You're not getting out, So this event horizon actually can be derived pretty simply, even without needing relativity. Is you could take this expression for the escape velocity, set the escape velocity equal to the speed of light, which is the fastest we think you could possibly be, and then you can solve for the radius, right? So 2gm, and then you set this to c. You can solve for r, and that defines what's called the event horizon or the Schwarzschild radius, which was named after Karl Schwarzschild, who actually derived all of this while he was serving on the Russian front during World War I. He actually mailed his derivations and his results to Albert Einstein, and Einstein actually ended up publishing his work for him because Karl Schwarzschild actually never returned from the front. He died of pneumonia while he was serving a few months later. But we now call it the Schwarzschild radius. So it's 2gm over the speed of light squared. So tell me the mass. I can look up g in a book. I can look up c in a book. I know 2. This gives me a physical radius, which we call the event horizon. And this is what we usually call the kind of the size of the black hole. And why that's a little misleading is because, again, remember that this is a bunch of stuff that gravity has caused to collapse down, possibly to a point. So it's not that the stuff collapses down to the event horizon and then stops, at least from the perspective of the matter that's inside the black hole. It might keep going and collapse even farther and farther down. But then there is this invisible location called the event horizon where if you pass by that point, you're not coming back out because then your escape velocity has now become faster than the speed of light. So no matter how powerful your rockets are, you're not going to be able to turn around and get back out. You always want to remain outside the event horizon. So that kind of makes it tricky because there's not like there's no welcome sign. It's not like the surface of the Earth where there's a clear location where it's the Earth and not the Earth. In this case, it's an invisible location that once you cross it, all hope is lost. Right? There's no welcome mat, but it would be an event if you crossed it. So you just don't want to get too close. You want to know what kind of massive black hole you're talking about, so you know how close you're allowed to get. So for the sun, this size is about, to give you a sense of the scale, the sun, this is about 3 kilometers in size. And so that there's no misconception here, that this again means that I would have to take the mass of the entire sun, and if I were to cram the entire sun down into something that was no more than 3 kilometers in size, the entire sun would become a black hole. Do not think that this means that the inner 3 kilometers of the sun is a black hole, right? The inner 3 kilometers of the sun is the core, right? That's where nuclear fusion is going on, where hydrogen is being turned into helium for our current day sun. But you have to take the entire sun and cram it down with some big giant vise. And if you were to cram it down to the size of 3 kilometers, the sun would turn into a black hole. For the Earth, same idea, about the size of a walnut. You would have to take the entire Earth and cram it down to the size of a walnut for it to turn to a black hole. Right? Remember, in comparison, we talked about how the sun, if you want it to become a neutron star, you have to turn it into something as big as San Francisco. If I kept going and crammed it down to the size of a walnut, then it would turn, if it turned into something that's about 3 kilometers in radius, it would turn into a black hole. For the Earth, you have to go down even more because there's not as much mass for the Earth. And then once inside, always inside. You know, what happens in a black hole stays in a black hole as a result. Don't want to get too close. And another misconception people have is that people think that, when they think of black holes, they think of these giant vacuums, where if the sun were to turn into a black hole, then the entire solar system would get sucked in and all the planets would be screwed. Not necessarily. Because remember, it's only when you're near the event horizon, or, heaven forbid, inside the event horizon, where black holes and all this strong gravitational distortions actually start to really matter. If we were to take the sun and turn it into a black hole without changing the mass of the black hole at all, actually nothing would change here on Earth. The Earth would still go around the sun once, or the now black hole sun, once every 365.25 days. Jupiter would go around, over its period, none of the planets would actually change or anything about their orbits. Now, of course, we would lose sunlight and the Earth would become inhospitable because it would get really cold. But in terms of as long as you're far away from a black hole, all is fine, right? You just don't want to get too close. Outside a black hole, gravity behaves perfectly normal, except when you're really close to the black hole, or again, once you fall in, you're not coming back out. Though black holes, when you are really close to the event horizon, you do start to notice interesting, weird distortions that you don't notice for, when you're looking near a star or looking near a planet. For example, this kind of distortion you're seeing in this image here, where all the light is kind of, kind of screwed up in a ring around this hypothetical black hole. Where it seems like you kind of can imagine if this was the Milky Way galaxy and there's a black hole nearby, seems like the entire image is kind of getting screwed up as a result. So what's going on here? We actually talked a little bit about this as well when we talked about relativity, that one of the main results of general relativity, or one of the big tests, the one that made Einstein an overnight sensation in the astronomical community, is that he showed that gravity can also distort the path of photons as well. Newton said, oh, well, you need, it's gmm over d squared. Two things have to have mass for there to be an attraction between them. Einstein said, actually, no. Massive objects like stars or black holes could actually divert the path of light as well. And this was tested in the early 20th century, where people noticed that light from distant stars, as they traveled nearby the sun, the path of that light actually bent as a result. I don't know if my mouse is showing up. I think it does want to do this. That light is being bent as it passes around the sun as a result. And they observed this during a total solar eclipse, so that the sun was out of the way. They could still see the stars. And they noticed that the stars were not in the locations they should have been at. Not because the stars moved, but because the light from the stars got diverted. So they saw the stars in a different configuration compared to what was supposed to be the case. This distortion gets even more extreme around black holes. So here's kind of the idea. You have kind of a field of stars. You're looking out. You're seeing some stars. And then what would this look like, the same image, if a black hole were to pass nearby? It might look something like this instead. Same stars, and the black hole's not doing anything to the stars, but the black hole is distorting the path that the light is taking as it tries to reach our eye. And so we get a screwed up, kind of messy image from light taking a diverted path, because it's coming close, not going in, of course, because you can't leave once you go in, getting close nearby and kind of looping around the black hole. You can show this it's kind of a fun little demo to do. You can show this if you have a wine glass that you've accidentally broken. If you use the base of the wine glass, you can, here's a kind of example of some stars and galaxies. And then notice as the glass kind of hovers over it, the image underneath gets distorted. You can see that the light is kind of smeared around, and kind of gets smeared around the center as a result. Let's do it again. Where again, nothing is changing about these objects themselves, but the path the light is taking can sometimes get screwy, and they kind of get looped out in arcs, or might even loop around the entire center of the wine glass. We call that an Einstein ring when we see this out in space. All right, so examples like, actually, let me go to, we can stick with this one. So the idea here is that, again, you have some distant object, and without a massive thing in between us and it, light travels from this galaxy more or less in a straight line towards us. But if instead there was a bunch of other things like black holes or other galaxies or things going around, all that mass could then cause the light from this distant object to get diverted around and kind of get pulled around and be brought back towards the Earth instead. And so that very, very distant galaxy, we don't get a chance to really see it as it looks, but kind of appears as kind of these distorted arcs, This is the very, very distant galaxy, but its light is being distorted as it tries to move around all these objects. And as a result, this actually can be very useful, because while we lose kind of sight of what the actual shape of the galaxy is, because it's these distorted arcs, this actually allows us a way of looking at very distant galaxies that would have otherwise been too faint. Let's just do this one more time. You can imagine if this were the case, only this one beam of light is really making it to the Earth. So if this galaxy is really far away, this is going to be very, very faint. Where if you have a more massive object that kind of bends light towards us, notice many, many more beams of light make it to us. So the more distant object that would have otherwise been too faint actually shows up a lot brighter in these images. And so we can see most of the most distant galaxies we've ever observed have been found through this sort of technique, We're seeing their light, we call it gravitationally lensed, around either galaxies or black holes or other objects for us to see. This also is kind of an idea of kind of what we're seeing here, where we've directly observed a black hole, where we actually think we have seen the location of the event horizon with a lot of extra material kind of flying around, or getting some of it probably getting bent around the edge of the black hole. And we're seeing a sort of silhouette of the black hole imprinted on the sky. So this would be one of the first direct images of a black hole in 2019. The vast majority of our knowledge of black holes have not been through direct images. We only have maybe a half dozen of these. It's very hard to see because they're very compact, very small. So you need them a very light, a very bright backdrop, if you want to have any hope of resolving these very tiny, compact, dark things. Right? That's why it's so hard. They're dark by definition, right? And astronomers can only see things by light traveling from it to us. So usually we have to infer their existence, unlike this image where we might have a more direct image here. It was actually kind of a fun thing, just kind of as a quick aside around these black holes. Once you get too close in, you fall in and you're gone forever. Even light falls in and you're gone forever. If you're far away from the event horizon, the path that light takes might get bent around the black hole. And then we can kind of see this kind of silhouette, of the black hole against this very bright backdrop. There's a location around the black hole called the Photon Sphere, which is about 1.5 times the location of the event horizon. So it's not too far away from the event horizon, but it's also not at the event horizon. So that's light can still kind of escape if it wants to. And it turns out there's a kind of a sweet spot where if I were to hang out near that region of the black hole and shine a flashlight kind of perpendicular to the black hole, it would loop around in a perfect circle and would illuminate the back of my head if I were located at that spot. Or, kind of more fun, if I were to take a mirror and hold up a mirror, the light from the back of my head would have looped around the circle of the black hole, and I might actually be able to see if I had a camera or a mirror or something like that, I might actually be able to see the back of my head in reflection if I were to try to look at myself, if I'm located at this photon sphere, because light that's coming off the back of my head would perfectly circle around and be matched back where my eyes are. I might be able to look at the own back of my head if I wanted to try to do that. This photon sphere is kind of a hypothetical thing because it turns out it's an unstable location. You give a photon a little bit of a nudge closer to the black hole and it will spiral in. Or if you give the photon a little bit of a nudge away from the black hole, it will spiral out and eventually escape. But there is kind of this sweet spot where you can trap light, which we call the photon sphere. I thought maybe it'd be a good way of kind of describing these tidal distortions and these light distortions we're seeing around black holes, and why this black hole kind of looks like this from light being bent around the black hole. That a good example to motivate this with might be the one from the movie Interstellar, Gargantuan, where it kind of seems like there's kind of this like a disk sort of thing here, but then it's also kind of illuminated on the top and bottom, so what's all this light and where is it coming from? So the idea here is that, or at least the motivation, and we have seen this actually happen around black holes, so this isn't completely science fiction or Hollywood movie magic, is that this light is actually the result of a disk of material that is orbiting around the black hole, but not too close, not in the event horizon, just outside the event horizon. Kind of like how we saw that when the sun formed, the planets all formed in this leftover disk that circled around a newborn sun. And we see a lot of evidence of this that we think, around black holes. You can also have these disks of material that have not fallen into the black hole, but might be kind of just orbiting around outside the event horizon. So if it were to shine light, that light could conceivably escape, and we could actually see it, just like how this image is kind of showing it. So the idea is, we think that it probably originated by, or how you might get an image like that, is if you have a massive black hole where, and this is kind of hard to see here, this little blue dot here is representing a black hole in the simulation. Then there's a nearby star that's going to kind of roam and kind of accidentally get a little bit too close to the black hole. Then the gravitational forces from the black hole are going to, as a result, kind of rip the star to pieces. This is a tidal reaction of force, just how we talked about why Saturn has rings. That material kind of gets smeared out and ripped into pieces around Saturn, and it creates a ring system. Same thing's happening here, where kind of light, or sorry, material from that nearby star. Let me zoom back out again. So here's the star, and then it gets whipped around and ripped to pieces. And then a lot of that material eventually falls into the black hole. But some of that stuff might kind of churn around and kind of get stuck in a disk that is orbiting around the black hole as a result. Same sort of idea of why Saturn has rings. But in the case of Saturn, it was tiny little pebbles that got ripped into pieces. Here, you might have an entire freaking star that gets ripped into pieces as a result. And so the interstellar black hole, if we want to think of it, right, we could they imagine that if you have a black hole that has a disk of material, right, so here's kind of a side view, or here's kind of a top-down view of material that's orbiting around this black hole, you could figure out if that material of light was glowing, where that light would appear relative to how we would see it, far away from the black hole. And as a result, you end up getting something like this. All right, so the front part of this thing here is the actual disk itself. It's in front of the black hole, but it's outside the event horizon, so that light is not falling into the black hole. It can still escape, and we see it kind of glowing here in the front. But then this stuff on the top and on the bottom actually is the part of this disk that is behind the black hole. And that light, as it's trying to move around the black hole on the top and on the bottom, kind of gets bent towards us. And as a result, kind of creates this illuminated halo that encircles the black hole. So the stuff on the top and the bottom is actually the backside of the accretion disk, the part that's behind the black hole. Obviously, that light can't go directly through the black hole to us, because then it goes through the black hole. But if it goes up and down, it can go and can get whipped around the black hole as a result of this idea that light its path can be distorted by gravity. And a lot of this for the movie Interstellar was actually worked out by Kip Thorne, who was a kind of frequent collaborator with Stephen Hawking, right? It's probably him and Stephen Hawking that really helped establish a lot of what we now know about black holes, at least up until Hawking's death. So he served as kind of the head PI, or principal investigator, or science consultant for the movie Interstellar. And actually, it turns out that Interstellar, they wanted to get the physics perfectly right when they were modeling these black holes. That this black hole actually is one of the largest, highest resolution simulations of a black hole ever done. Just through the power of Hollywood, the power and money of Hollywood, the calculations they did to get this image really does perfectly incorporate Einstein's general theory of relativity and how that causes us to perceive a black hole from a distance. And then similarly with things like, if you think of the movie, how time kind of gets screwed up in certain places when you're nearby a black hole. We'll talk about that in a little bit. But all of that is really deeply rooted in physics. There's a great book that Kip Thorne published. I forget what it's called. I think it's just called like The Physics of Interstellar or something, where he kind of breaks down the different kind of physics in the movie and tells you kind of what's legit and what had to be made up. Turns out the vast, vast majority of the astronomy stuff actually is deeply rooted in science. It was really only the kind of inside of the black hole stuff and this kind of the plight or whatever they called it, that was eventually destroying Earth. That stuff had to be more made up, but the physics part actually pretty good. And one of the images they have in the book actually kind of shows exactly what I was just saying. How you can imagine you have an accretion, the disk around the black hole, and it's kind of color coded, kind of the different sections of the accretion disk. And then it shows you kind of where these different parts of the disk appear around the black hole. So like these parts here kind of match these colors here. So the front of the disk then appears in front of the black hole. But then this part here, these colors are corresponding to kind of these parts right here. So we're seeing a combination of things that are kind of from the behind of the black hole and then in front of the black hole as a result. It's kind of cool. And again, these are just distorted effects of when you get too close to a black hole, but don't fall in, light can take kind of a weird deviated path and create these distorted effects. So actually, a comment I'll make actually is that people think that these black holes, I mean, admittedly, very smart people like Stephen Hawking and Kip Thorne and others have thought about black holes and have thought about the intricate physics about what's going inside the black hole, which is very hard because we can't test what's going on inside of a black hole. It's almost outside the realm of science because we can't do experiments with the inside of a black hole because there's no way we can actually go collect data. If my TAs go into the black hole, collect data about what's going on, they can't get back out to come tell me so we can publish our paper. So anything that's going on inside the black hole, right, really is a mystery to us. And people come up with ideas and theories, but it's tricky because we have no real way of ever being able to test these things. But at least around the vicinity of a black hole, people have worked this out, and there's something called the no-hair theorem. And it turns out that while what's going on inside a black hole might actually be fairly complicated, how the black hole interacts with its environment actually is pretty simple. So the no-hair theorem is saying that a black hole's properties are entirely determined by its mass, charge, and how much spin it has, or what we would call angular momentum. That if you tell me those three things, I can tell you exactly how the black hole behaves and operates and what it does in its local region of space. There's nothing else I need to know. So we say that a black hole has no hair. And this is the idea, like imagine you have the Earth, right, which is the mass of the Earth, and Earth looks very, very particular. But you can imagine that somewhere else in the galaxy, there is another planet that has exactly the same mass as the Earth. So it's exactly the same size and mass as the Earth. But it likely on its surface looks vastly different than our Earth looks here in the solar system. So I can't uniquely describe an object with the mass of the Earth by only its mass and maybe how fast it's spinning or whatnot, because we have trees and nature and people, and who knows what that planet has out there. But for a black hole, really, it's very, very simple. Tell me how massive it is, tell me if it's spinning or not. The black hole in Interstellar, for example, had to be, in order to get the physics right, it had to be a very rapidly spinning black hole. That's okay. We think that's easy enough to explain. Stuff is falling into the black hole. If it kind of falls in at an angle, or you can imagine slapping someone on a merry-go-round, or if you slap them at the right time, you can speed them up, and up, as a result of. So it makes sense that the black holes could possibly be spinning. They have a mass, which tells me how gravity operates nearby. Then also it might depend on the charge. But we actually think this charge probably doesn't even really matter that much. Because if I had a black hole that had more protons than electrons, say, it would have a positive charge, but then positive charges attract negative charges. So we think that actually if you had a positively charged black hole, it would attract nearby electrons that would then fall into the black hole, and eventually the black hole would become electrically neutral. So while we can't rule out that a black hole can have a net charge, we don't think it actually matters that much, so that it would equilibrate pretty quickly. Just like how the Earth more or less has a no net charge. There's about the same number of protons as electrons. Because again, if there was an offset excess, it would attract nearby protons or electrons from space until everything kind of balanced itself out. And then it would just be gravity trying to pull things in, but gravity doesn't care if you're charged or not. So it would pull everything in kind of, equally. So that's kind of the no-hair theorem. So it doesn't matter at all what you throw into the black hole, right? You only care about its total mass, right? You can throw encyclopedias or your arch enemy or the Bible. It doesn't matter at all what goes into a black hole. All you care about is how much mass there is in total and whether or not it's spinning. We'll come back to spinning. Spinning can actually have some interesting effects. And maybe there's a charge, but again, we don't really think it matters at all with charge. Let me talk about kind of what happens if you hang out near a black hole. So again, we don't want to go into a black hole, but what if you were to hang out near a black hole? What issues what should you worry about in that local vicinity? Well, this region, you're feeling likely some strong gravitational forces because you have a lot of mass inside the black hole, and it's compact to a very, very small volume. So if you just think of Newton's gmm over d squared, the m is huge, and the d is very small. So you got two factors that are both adding up together to make the gravitational forces acting on anything nearby a black hole pretty extreme. And so you can get this thing called spaghettification, and this is the technical term. You can look up, there's a Wikipedia page, for spaghettification, of how if you were to hang out near a black hole, you would feel yourself get stretched like a big noodle of spaghetti, as gravitational forces would try to stretch you out from head to toe. And that's fine, again, as long as you don't get too close to the black hole. And the idea here, actually, of what's going on here is the same exact reason that we talked about regarding tides from the moon on the Earth. These are tidal forces. So again, remember the fact with the moon is pulling on the Earth. The moon is also pulling on the water on the near side and the water on the far side of the Earth. So why there are two high tides is because the moon is pulling on different parts of the Earth with a different amount of strength, because it depends on how far away you are. So we argued that there must be two high tides because the moon is pulling on the water on the near side with a large gravitational force because it's closest to the moon. So that water, in a sense, is kind of being lifted off the surface, if you want to think of it that way. Then the moon is pulling on the Earth, or pulling on water that's kind of in the middle locations on the surface of the Earth, but with not as much force as the water droplet on the near side. Then similarly, the moon is pulling on the water droplet on the far side of the Earth with the weakest amount of force because it's farthest away from the moon in this instance. And in this case, why we think that there's a high tide, actually not why we think, why we know that there's a high tide on the far side of the Earth, is that essentially this water is being pulled off the surface towards the moon. The Earth itself is being pulled towards the moon with a strong force, but not as strong as the water on this side. And so as a result, this water is kind of getting left behind. As the Earth kind of moves towards the moon, this water gets left behind. And so it appears, from our perspective, like the water kind of rises off the surface as a result. And so you have two high tides on the near and far side of the Earth, or one high tide roughly every 12 hours, depending on your location on the Earth. Same idea with these spatial distortions, but to the most extreme limits. If you're hanging out near a black hole and your feet are kind of near the event horizon and your head is far away from the event horizon, your feet are closer to the black hole than your head. So your feet feel a stronger gravitational pull towards the black hole compared to your head. So as a result, you feel your feet being pulled away from your head. So you feel your neck being stretched. And if you do the 2D analysis of this, you also feel yourself kind of getting squeezed inward and everything kind of gets pulled in towards the center of the black hole. And you feel yourself stretched out or elongated like a noodle. So this is called spaghettification, these spatial distortions. And of course, you don't want to get too close, right? If you're outside the event horizon, all is well. But also, if you get too close, right, it might be that you're feeling yourself stretched so much, you might be more concerned about being ripped to pieces. So actually, kind of interestingly, it is actually safer to go study supermassive black holes, things that are millions of times the mass of the sun, like the one in the center of the Milky Way. It is actually safer to go hang out outside one of those black holes compared to going out and hanging just outside one of the tiny little stellar mass black holes because of these tidal forces. Here's kind of the basic idea. If I send Kaylin and Justin to go study black holes, Kaylin has to go hang out near a small black hole, but Justin has to go hang out near the massive black hole in the center of our galaxy. It actually turns out Justin will fare much better than Kaylin would. And again, the idea is that even though you have less mass that makes up this black hole, your height, or the kind of the relative size of you compared to the size of the black hole, is actually more comparable for a small black hole compared to the size of Justin compared to the size of this big old black hole, which you think is about the size of the solar system in the center of the Milky Way, compared to one that's the size of, say, a few kilometers for a small black hole. And so since it depends on the distance from the center squared, if we use Newton's law of gravity, the difference in the gravitational force at Kaylin's feet, when it's a very, very small d, to still when there's a pretty small d, the difference between the feet and the head, since d is already pretty small to begin with, is actually more extreme in this case compared to if you're outside a big old black hole, right? You're millions and millions of miles away to get to your feet, and then you're millions and millions of miles away plus 6 feet to get to the head. You know, the size of your body compared to the distance between the center and the edge of the black hole really is nothing. So Justin feels more or less the same pull at his feet compared to the amount of pull he's feeling at his head. So he doesn't feel himself stretched out like a noodle, where Kalen actually would have to be a little bit more concerned about being stretched apart or ripped to pieces, you know, depending on how close he is. But kind of a fun, kind of non-intuitive, you would think more massive, more havoc it will wreak. But again, as long as you're outside the event horizon, actually it's safer to hang out around these big massive black holes compared to the small ones. Because again, the distortions become so extreme, mostly because the denominator gets so small. Large gravitational forces outside small black holes. That's spaghettification. And that's kind of how space can get screwed up around black holes. What about time? Here is where it gets really interesting, but very, very non-intuitive. So we have to talk a little bit about general relativity real quick before you can kind of fully appreciate what's going on here. So Newton, when he came up with his laws of physics, right, he had an idea that there was kind of some universal big grandfather clock somewhere in the universe where essentially it dictated the passage of time for everything in the universe. Everyone in the universe could, if they synced their watches with this big clock that Newton, imagined, everyone in the universe, no matter who you are or what you're doing, would all agree on the passage of time. Right? I would say that time passes in 1 second per second over here, or some alien on the distant edge of the galaxy would also say that time is passing 1 second per second, or someone else that's hanging out near a black hole would say that time passes 1 second per second. It would not matter what you're doing or where you are, everyone would agree on universal time, according to Newton. Einstein said, actually not quite. His idea of space-time actually revealed, when he came up with special and general relativity, that if you screw around with space, you also end up screwing around with time. And you can ask if you want to know the details. It related actually to the fact that he realized that the speed of light must be the same no matter who observes the light moving. No matter what you're doing, you always measure the speed of light traveling at the speed of light. Even if you yourself are traveling at, say, holding a flashlight and running at 99% the speed of light forward, you still see the light come out from that flashlight at the speed of light, not, say, 1% the speed of light because of the relative motion. So that actually was a big motivation behind the ideas of relativity. But when you take that to its natural conclusion, it reveals that everyone has a unique perception on how time passes. What I think is 1 second per second is not the same as what someone else will say is 1 second per second. And depending on what we're doing or what we're hanging out nearby, if we're hanging out nearby black holes, or if I'm running around at half the speed of light, we all would come to a disagreement on how time is passing. It's a relative effect. Makes sense. It's part of the general theory of relativity, that our perception of time is a relative effect. If we all got together in Galileo Hall and synced all our watches, and then we all went off and did vastly different things with our lives, some went near black holes and some, launched themselves into spaceships and traveled in circles around the Earth for the rest of their lives, and then we all came back together 80 years from now, none of our clocks would be in sync. All of them will have ticked different amounts, and we would have perceived each other to have aged by a different amount. Kind of weird. This is weird because we don't actually notice this from our vantage point. We're hanging out on Earth, which is not very massive, so we don't really get any weird distortions from the mass of the Earth. And we also are not moving very fast either. Turns out that if you move around, that actually can screw things up as well. Though this has been experimentally verified. It's not that this is all just make-believe. There's these, one of the most famous experiments is that there's radiation called cosmic rays out there in space, and the sun emits some of this too, that when these cosmic rays hit the atmosphere of the Earth, they create these things called muons. And these muons then kind of, shower down to the surface of the Earth, tiny little energetic particles that are moving pretty close to the speed of light, but not quite. However, they only live for about a microsecond. These muons, after about a microsecond or so, just decay and burst back into other things. So you can calculate that if these muons are being created at the surface of it or at the top of our atmosphere, they actually should more or less entirely decay before they make it to the ground. We should not really see any muons making it to the surface. But when we get our little muon detectors and hold them out near the surface of the Earth, we notice that there's bunches of muons making it to the surface, even though they should have decayed, according to us, standing on the Earth. So how you fix that actually is that since these muons are moving very, very fast, the rate at which their stopwatches are ticking, which, once they hit a microsecond, they disappear. The rate that their clocks are ticking is actually much slower than the rate that our clocks are ticking here on Earth because of their motion. So as a result, the muon only thinks maybe a tenth of a microsecond passes by the time it takes it to go from the top of the atmosphere to the ground. Where we would say, so as a result, it survives, at least from our perspective. That's where this gets really tricky. You always have to say kind of from what perspective you're observing things at. Because the muon actually turns out to go really into the weeds. The muon actually thinks that its time always ticks normal. You always see your own local time ticking normally. If I have a watch and I stare at it, no matter what I'm doing or where I am, I always see my clock ticking at 1 second per second. But if I look out into the universe and look at other people that might be doing other things or might be hanging out near black holes or whatever they're doing, I would notice that their clocks are actually possibly ticking at a different rate than mine. And then they would see their clock ticking at a different rate than mine as well. It's very weird. But you always see your own local time ticking normally. You always count 1 second per second. 1 Mississippi, 2 Mississippi, 3 Mississippi. But then I might look out and see someone, Kalen hanging out near a black hole, and I would see his clock actually ticking much slower, right? Where I would count in the amount of time it takes 5 seconds to pass for me, maybe only 2 seconds passes for him, just by looking if I zoomed in on his watch or something like that. Or I would see him kind of moving in slow motion. And so the idea is that we see these muons essentially kind of, they age in slow motion. And so enough time does pass, according to us, for them to make it to the bottom. And it turns out what the muon perceives is that they see actually the distances kind of get screwed up. The muon thinks the atmosphere is actually not as thick as we think the atmosphere is. So they have less distance they have to travel. So they know they can only live for a microsecond, but they can easily make it to the surface over a shorter distance compared to what we think the distance they have to travel is. It's very strange and fun. But again, these are experimentally verified things. We have seen that by putting very, very hot, fancy clocks on airplanes and whizzing them around the Earth, we can see that the clock that started in sync with the Earth gets out of sync as it whizzes around the Earth. And, it's a very, very slight effect for us because we're not traveling near the speed of light and we're not near a black hole or anything like that. But we have measured this. GPS actually would not work if you did not take into account these differences in how time ticks for the satellite up in the atmosphere compared to us here on Earth. It has to take into account both the fact that the satellites are moving, that's special relativity, and the fact that the satellites themselves are farther away from the Earth compared to us on the Earth. Our clock on Earth ticks a little bit slower compared to the clock on the GPS satellite from the satellite's perspective. Kind of fun stuff, but every time you use your Maps app that relies on GPS, thank Einstein. So here's kind of a summary of some of the things that are happening, right? If you were to hang out far from a black hole or near a black hole, different things happen. So suppose, so in this case, you can kind of see that, so kind of the general takeaway is that clocks tick slower if you're nearby a black hole or nearby a massive object. They don't tick quite as quickly if you're hanging out near a black hole compared to if you're far, far away from a black hole. And that relative difference allows for some interesting things to happen. So again, if you're far from a black hole, what do you see? Right, so I'm far away from a black hole looking towards someone hanging out near a black hole. Right, maybe I'm hanging out far away from the black hole and Kalen is hanging out next to the black hole. I would see Kalen moving in slow motion. All the while my clock is ticking normally. 1 Mississippi, 2 Mississippi, 3 Mississippi. Nothing seems wrong to me, but I would see Kalen essentially moving in slow motion. All the while, any light that's coming from him would also be gravitationally redshifted. That's just a detail. But then for the exact same situation, what would Kalen see? If Kalen is looking at me while he hangs out near a black hole, he would look at his watch and not see himself moving in slow motion, but he would see his clock ticking at 1 second per second. 1 Mississippi, 2 Mississippi, 3 Mississippi. Nothing would seem off to Kalen about himself. But then when he looked out to me, it would look like I'm kind of whizzing around at 2x speed. I would be whizzing around at much faster. And if he were able to see my watch, it would the hand on the clock of my watch would seem to be going very fast, even though I would see my own clock ticking normally. But Kalen would see my clock ticking much faster. And then it's reversed. I would see Kalen's clock ticking slow, where my own watch would appear normal. So it's a relative thing. So non-intuitive, because we're all used to being able to sync our clocks and always we can all agree on what time it is. But technically that's not true. We all have our own unique clock that gets slows up and slows down depending on what we're doing or what we're hanging out nearby. Gravity slows down time. So if you hang out near a black hole, your clock, at least relative to someone not near the black hole, will see you ticking, moving kind of in slow motion. Right, so this is not a way for you to be able to read more books or go to more movies or send more tweets over the course of your life, because you always perceive your own time as normal. You just see the rest of the universe behave differently. If you're near a black hole, you see the rest of the universe kind of on fast forward speed. If you're far away from a black hole looking at someone hanging out near a black hole, they appear to be moving very sluggish for some reason. Though they don't know that they're moving sluggish, they just appear sluggish to you. So something fun can happen if you play around with the idea of, suppose you want to throw your mortal enemy into a black hole. What would you actually see? And what would your mortal enemy see as they got closer and closer and closer to the black hole, and then eventually fell in and passed through the event horizon? So let's take this with a hypothetical example of, let's suppose I and Justin are hanging out and I've decided that Justin is my mortal enemy. And I, the being of all that is good in the world, am hanging out near a black hole. But then Justin decides that he is going to throw me into a black hole and just be done with me. Maybe I didn't give him a good midterm score for upper level astronomy. So what would happen if I were to fall into a black hole? Let's first do from Justin's perspective. So initially we would agree on the time. Let's suppose that this event happens at noon. At noon, he gives me a kick and I start falling into a black hole. So at the very beginning, we would both agree on what time it is. But as I fall towards the black hole, as long as I'm still kind of far away from the black hole, time is ticking normally, right? So I don't notice any major difference between my time and Justin's time, and Justin doesn't really notice any difference between my time and his time, as long as I'm still decently far away from the black hole. However, as I get closer to the black hole, from Justin's perspective now, he notices that my clock is starting to tick slower relative to his. So while he might think 3 hours have passed, he will have only seen maybe 2 hours pass for me. So as I fall towards the black hole, which you might imagine would make me kind of start to move faster and faster and faster as gravity kind of pulls you down, he actually sees me start to slow down as I fall towards the black hole. Not because I'm trying to get out, but just he sees the click of time slow down. So rather than me speeding up towards the black hole, he actually sees me start to move slower and slower and slower. And this gets even more extreme as I eventually reach the event horizon. And it turns out, from Justin's perspective, he never actually sees me enter the black hole. The amount of time that he sees pass for me gets so slow that essentially it goes to infinity at the event horizon. So he never actually gets the pleasure of seeing me fall through the event horizon. He sees me get closer and closer and closer and closer to the event horizon, and then I just slow down to a halt. And then I just kind of freeze right at the event horizon. Now I might be kind of stuck in some sort of like screaming terror, but whatever I was doing right as I crossed the event horizon, he would see that one singular image for the rest of time. And then as the light gets redshifted, he might see me kind of gradually fade away, but he would never actually see me kind of fall through the black hole. People actually thought of this when they first were working this out with general relativity. And we did not call black holes, but we thought that if you had a star that collapsed in on itself to be a black hole, they had worked out that actually the stuff that's right outside the event horizon, right, we would see it not fall in to become a black hole, but it would just kind of freeze at the event horizon. So you would see kind of the star kind of in a state of collapse, but then it would just be a freeze frame of when it actually finally turned into a black hole. So another term for these things, we called them frozen stars. Not frozen because they're cold, but frozen in that we actually would see the implosion kind of freeze frame, and we would see it kind of in the middle of its collapse rather than actually seeing it collapse. Right? Movies get this wrong all the time. Right? One that kind of comes to mind is like the first of the new Star Trek movies where, spoilers, the planet Vulcan gets turned into a black hole through some sort of device. And never mind how that's possible, but they show in the movie, right, the Enterprise is kind of whipping around the planet, and then they show the entire planet just kind of collapsing on itself to form this big massive black hole in the center. Wrong. Completely wrong. What they would see is Vulcan would start to collapse in, and then it would just kind of freeze in a state of collapse. So they would see all the screaming people kind of just stuck in, in this kind of a still image of them as it was all collapsing in. So you don't really get the satisfaction of seeing your mortal enemy fall into a black hole in this regard. Now what happens from my perspective? Justin gives me a kick at noon. What do I see as I fall in towards the black hole? He saw me slow down, eventually freeze. Of course, at the beginning, we kind of both still agree on what's going on. I'm far away from the black hole, so I think an hour has passed as I fall. He thinks an hour has passed as I fall. My time note, now since this is from my perspective, I feel time always ticking normally. So after another hour, I am continuing to get faster and faster and faster as I fall towards the black hole. I feel myself speeding up as gravity pulls me closer and closer and closer to the event horizon. But then I notice when I look at Justin far away from the black hole, I notice that he's not just cackling at normal speed, but he's cackling in kind of a fast forward speed and kind of just whizzing around. So I might notice that his clock is running very fast. He's in kind of fast forward motion. All the while I'm feeling myself just kind of fall in at a normal speed. And again, I'm speeding up. I'm not slowing down from my perspective as I fall in. Then as I get closer, it gets more extreme. Or I think 3 hours have passed. To me, it looks like Justin has gone through 6 hours of cackling during this entire process. I eventually reach the event horizon. Justin's clock is becoming incredibly fast, right? I've seen him leave and come back, right, and have a picnic and go do other things, right, and take his other final exams. I've seen him gone and have days and days worth of living. All the while, only an hour has passed. I'm seeing him at exceptionally high speeds. And just how, like, from his perspective, he essentially sees time come to rest at the event horizon. I see the opposite, where I see time go faster and faster and faster. And technically, as I cross the event horizon, I see the entire universe perhaps flash before my eyes. Essentially, time becomes infinitely fast everywhere else in the universe. So I at least get to go out with a glimpse of what might happen through all of space and time in the flash of an eye as I cross the event horizon. So I actually, while Justin never gets the satisfaction of seeing me fall in and die, I might actually get the satisfaction of, as I'm crossing the event horizon, where my life is going to get much more, it's going to take a downturn, I guess, moments later after I'm over the event horizon, but I at least will get to see everyone else flash before me, right? So I might actually get to see Justin pass away from natural causes compared to what he gets to see from his perspective. And again, it's this asymmetry of how we perceive time. Near black holes, right, there's a slowdown relative to Justin. So then if I'm near the black hole, I see everyone else kind of whipping around as a result. Kind of fun. Now, imagine this case where I'm getting close to the black hole. I have not quite fallen in yet. So I'm still outside the event horizon, so I can still escape. Now suppose I have hidden a rocket under my cape and I escape from the black hole and turn around and come back to Justin. What could happen then? At this point, I think 6 hours have passed for him, while he only thinks 3 hours have passed for me. And maybe it takes me another hour to get, to turn around and go back to Justin. Well, in that case, I might get back to Justin and I will have only perceived on my own watch, which again is ticking at 1 second per second for me. I will have only seen myself age about 4 hours. All the while I have seen Justin age about 8 hours. And I can then imagine everyone else, which is also far away from the black hole, that everyone else has aged 8 hours while I've only aged 4 hours because of this event. Well, I've time traveled. I've jumped 4 hours into the future, right? If I define the future as the time that everyone else has agreed upon, because they're far away from a black hole, they're all not moving very fast, they can all kind of sync their watches and they more or less don't get out of sync. But then I can go hang out near a black hole, only age for 4 hours, come back. Everyone else will have aged for 8 hours, but I've only aged 4. So in a sense, I have jumped 4 hours into the future. So it's possible that you can time travel using black holes. Unfortunately, it's one way. You can only time travel into the future. If you go out, hang out near a black hole, everyone else is on fast forward motion, then when you eventually come away from the black hole, you will not have aged as much as the rest of the people in the universe, right? So you have jumped into their kind of collective future as a result. So you can time travel if you go hang out near a black hole, right? So, but you can only move forward. There's no way that the opposite asymmetry can't occur. You can't hop into the past as a result, or at least be able to redefine events that have already happened, right? You might think in a sense, Justin is kind of leaping into my past. But in this case, really, not really, right? Because if you define the past as a series of events that have already happened, no, I haven't had events that he could then go back and, change, right? Like how you can't go back and kill your mother or something like that. So it's not really a backwards time travel in that case. Really, I've only time traveled into his future. He can't time travel into my past because of this weird kind of time asymmetry. It's kind of fun. Here's something I usually don't talk about, but since it's a recording, why not? I think your book talks about this a little bit too. For rapidly rotating black holes, there's actually this fun thing that can happen around a black hole called the ergosphere. So again, the example of the interstellar black hole, to get the physics working out just right, I think it turns out that this thing has to be a very rapidly rotating black hole. And they can work out kind of, in order to get this image, which again, they wanted to be based in science, the black hole also had to be very rapidly rotating. Some interesting things can happen actually if you have a rapidly rotating black hole, because think back of the times we've talked about rotation, where you have something that's rotating, and just like if you're in a merry-go-round, right, if it's a really fast spinning merry-go-round, you feel yourself being thrown out towards the edge. And so the same thing happens if you're trying to loop around a very rapidly rotating black hole. There's that kind of merry-go-round force that's throwing you out, even if you're near the vicinity of a black hole. And so there's this region that ends up getting defined, which we call the ergosphere, which is kind of in between the event horizon and where the event horizon would have been if the star was not rotating. We talked about how the event horizon is kind of the point of no return. But you can imagine if you have rotation, that is kind of working to help you to also throw you out away from the black hole. So it turns out if the black holes are rotating, you can actually get closer to the black hole than you could if it weren't rotating. And kind of the region in between the new event horizon and what it would have been without rotation, we call the ergosphere. And funky things happen in this region because this is a region of space where essentially the black hole itself is whipping space around itself. Like you imagine like the sun is whipping the planets around, but the planets are kind of moving on top of space as the sun kind of whips them around from gravity. The black hole, you can think of like space as just a big tarp or grid. The black hole is actually pulling the fabric of space around with it, and it's kind of getting whipped around the black hole. Some interesting things can happen once you get into these possible regions. But kind of a fun thought experiment of people that have worked this out is that these ergospheres actually could be a way to solve both our energy and our garbage issues all at once. So you can imagine a civilization that has two problems. It has a lot of garbage and nowhere to get rid of it, and it doesn't have enough energy, right? A very technologically advanced civilization needs lots of energy that it can't generate on the surface. There's actually a way that you could fix this problem with black holes, where the idea is that if you could get a garbage truck or a garbage space truck, fill it with garbage, and have it kind of just soar and careen towards a black hole. Not falling into the black hole, but have it kind of loop around through the ergosphere. And you can work it out that if you have the garbage truck kind of whipping through the ergosphere, that once it gets to this point kind of in the center, it could then dump all its garbage into the black hole and just dump its garbage out, and all that garbage would then fall into the black hole. You can work out the physics that as a result, the garbage truck actually ends up leaving the ergosphere because the black hole is whipping everything around, including the garbage truck. The garbage truck ends up leaving the ergosphere with more energy or at a faster speed than it entered with. So it has both gotten rid of its garbage and it's left the region around the black hole with more energy than it started with. So then you could imagine this very fast now moving garbage truck gets back to Earth, and maybe we just have it, move through a bunch of, turbines or windmill-like things, as it runs through them, makes them spin. That would slow the garbage truck back down, but that's okay because we got a boost of energy from the black hole for free. And then that energy that goes into the spinning turbines, kind of like a windmill, can then be turned into other kinds of energy that we could then use to power our buildings and whatnot. This actually is an idea, right? This seems kind of silly, but like this actually is kind of rooted in, observations where we think we have observed something like this, where it actually supports the idea that this is actually happening. Not, of course, in the case of intelligent life throwing garbage into a black hole. But we actually have seen when we look around distant black holes that we think those black holes have very fast-moving accretion disks that are just outside the event horizon. We can calculate how bright we actually expect those accretion disks to be based on how much stuff there is and how fast they're moving. And around some black holes, we actually see evidence that this material is moving faster than it should be, at least based on kind of normal classical calculations. So it does seem like as this stuff is whipping around a rapidly rotating black hole, that some of that black hole's rotational energy is being given to the material. And so as a result, it moves faster and ends up glowing a little bit brighter than we would have expected it to be. So we do think we have actually seen evidence of this. And I think we've actually done something on Earth where, again, the effect is very, very minute on Earth, but we have seen this sort of similar kind of effect, I think, as things try to whip around the Earth. So there it's a little bit more debatable. Really is more evident if you're very close to a black hole and dealing with very, very strong poles where you can kind of get pulled in, dump your trash, and then whipped out with an even faster speed than you came in. Kind of cool. All right, two more things, or three more, or maybe 2.5 more things. With these severe distortions in both space and time across this fabric of space that we call space-time, and we think it's happening in all 3 dimensions, really all 4 dimensions, if you think space is 3-dimensional and then time is an extra dimension. Why not others too? If we do live in some sort of multiverse or some sort of big hyperspace where there's other dimensions we don't know about, why can't gravity have these similar kinds of distortions in those dimensions as well? Well, this is kind of the basic idea behind a wormhole, which actually was first used by scientist John Wheeler, a theoretical physicist. These things appeared first in papers, not in science fiction. The idea that you could have a distorted part of space where, if we live in a multi-dimensional hyperspace that's bigger in dimension than what we're familiar with, it's actually conceivable that you could have, for example, if you had a big black hole here that kind of made a big distortion in space-time, that it could connect to a different part of space in our own universe, or maybe if there's if we live in a multiverse, maybe across dimensions to 2 universes. And you have probably kind of seen something that looks like this. I will use Mitchell's athlete release form. All right, so if you imagine this is our universe and people can kind of roam around on this piece of paper, right? We really don't know if the universe is a flat sheet of paper or if it kind of can be looped over like this or maybe twisted, right? We have no kind of observational evidence of kind of the shape of our universe in this regard. So it's possible that you could have a universe that's kind of looks like this, but we can only move in the paper. We can only move along the paper. So we don't really know whether or not it's bent or not. Then you could imagine that if you had something like 2 black holes that were linked together across this new in-between dimension, right, then kind of can pierce it through, then maybe in this case, there is a way for someone to get from this location here in our universe, and while they would have to normally kind of travel along this entire distance to get to this point, right, maybe instead they could kind of travel through some sort of wormhole to get from this spot to this spot. So you're kind of traversing a dimension you don't normally have access to, but theoretically possible. It's not completely ruled out by the laws of physics. It's not something that science fiction just came up with. These are theoretically possible. The sad news is that they probably don't exist. You can work out the stability of something like this where, well, one, you first have to deal with if you're going into a black hole and exiting another black hole, which sometimes we call a white hole. You first have to be able to, whatever you are doing, you have to be able to deal with those strong gravitational tugs and pulls you're going to experience while you go through, which probably is not going to be very fun. But even that aside, turns out you can work out the idea that if you did have kind of a bridge between 2 spots that were connected by 2 black holes, it ends up that they end up being very, very unstable. So it's unlikely that they would actually, if these sorts of things do exist, they would only exist for a little bit and then probably disappear. So the idea of like having these big wormholes, like an Interstellar, for example, like that probably is not, that likely is very impossible to do, because that wormhole, even if it did exist, but it essentially would have gone unstable and collapsed in on itself almost immediately after forming. So that would mean you would need something like some sort of like weird sort of exotic matter that kind of keeps the throat of the hole open, which we have 0 evidence that any sort of matter like that could exist. Some people think this weird thing we'll talk about called dark energy could be a way of doing it, but again, it seems highly unlikely that you could get something like a wormhole that could actually exist. But kind of fun to think about. All right, let's see. I think for the sake of time, I will skip the discussion on kind of how we detect black holes, since we talked about that in class. Again, the basic idea being that you can't just look for black spots in the sky. Is this a black hole? Is this a black hole? We, up until a few years ago, didn't really have any direct evidence. Now we can see a couple of these black holes and actually have direct evidence. But usually the short answer is, I guess I just said I wasn't going to do this, but here we are. The short answer being is that we usually can infer the presence of these black holes, be it that there's gas around the black hole that's outside the event horizon that we can see. Like usually we see this in kind of X-rays or gamma rays. So kind of one idea we think of how you might form black holes is that maybe you have two neutron stars that are slowly but surely spiraling in on one another. And once they merge together, there's something that's too big to be held up by the neutrons, so they become a black hole. But right before they kind of do that merge, they kind of smash into one another, and we think you might get something like a gamma ray burst. Or we think that you might have massive stars that as a massive star kind of collapses into a black hole, it might also launch a gamma ray burst. So there's a whole branch of astrophysics that's based on entirely just looking at the sky and trying to find these things. Because we think these gamma ray bursts might be kind of the birth cries of black holes, right? Black holes that are just coming into existence for the first time, either through a big star collapsing or through something like two neutron stars merging together, something like that. And then similarly, the evidence that we have that there is supermassive black holes or black holes in the center of our galaxy also is not because we can directly look at the black hole, though there have been observations, again, in the last couple of years, I should have put a picture of it in this, where we do think we have gotten kind of a more direct image of the black hole in the center of our Milky Way galaxy. But up until a few years ago, right, we have instead really just been inferring that the black hole is there based on what's going around with stuff around it. Right, the idea being that we can see stars near the center of the Milky Way galaxy. And if we track them over a decade or so, like Andrea Ghez did in the 90s and the aughts, she saw that there were stars that often were kind of looping around this kind of invisible central point that we put the little red cross by. Whereas something gravitationally is causing these objects to move around in elliptical orbits. It kind of looks like ellipses, like we talked about with Kepler's laws. And you can figure out and calculate how massive must this thing, whatever it is in the center, be, such that these stars are whipping around at the speeds and at the distances we can see them moving at. And you get something that's about 4 million times the mass of the sun. And since we have no possible idea of what an object that is 4 million times the mass of the sun could be other than a black hole, we do really think that this thing must be a supermassive black hole in the center of our galaxy. And we think most galaxies, the vast majority of them actually, do have a supermassive black hole in the center. These things likely formed when the universe was very young. A lot of big black holes likely formed when the universe was very young. Galaxies were taking shape for the first time. They did not build up from a bunch of stars colliding or anything like that. They probably started really big. And then there are the little black holes that kind of roam around the galaxy as well. A lot of this work was done by Andrea Ghez, now at UCLA. And she won the Nobel Prize. She and others won the Nobel Prize for this sort of work in 2020. Okay, last topic. Up until now, I've really only been talking about black holes classically. I have not had to invoke quantum mechanics, the physics of the very small. But it turns out when you start to consider quantum effects of what might be going on in the quantum realm around or near a black hole, actually some more interesting things can start happening near black holes. And actually it turns out, as was first theorized by Stephen Hawking in the 70s, is that actually I might actually be incorrect when I say that black holes are one-way trips. That might not be entirely true. It might be possible that it actually is theoretically possible that things that go into a black hole might be able to eventually escape as a black hole, albeit not in the same shape that they came in. If I throw myself into a black hole, I might eventually escape the black hole, but I would probably escape as a bunch of electrons or protons or photons as a result. I wouldn't actually be able to just walk back out of the black hole. So this is the idea behind Hawking radiation, or the idea that black holes might evaporate. Stephen Hawking first came up with this idea in the 70s, and really would be Nobel Prize worthy if we've detected it. Unfortunately, we have not found any evidence that this actually is true. but there's a lot of theoretical support that suggests this might actually happen. And actually, it turns out that if this does happen, it happens exceptionally slowly around normal black holes, such that it actually is very hard to fathom how we could actually observe this very faint evaporation that's going around black holes. So he wrote about this a lot in his kind of very popular book, A Brief History of Time, which, with all due respect to Hawking, which I've told you I've met him a few times when I studied in England, so I consider us best friends. This might be the most bought but least read science book of all time. It was written intended for a popular audience where you didn't have to be a physicist to understand it, but after about chapter 3, it really gets very complicated that even physics majors would have a hard time kind of making it through. So he then came up with an easier version called A Briefer History of Time, but that I think he actually kind of overshot. I would say I would not recommend you guys get it because I think after taking Physics 90, you actually know as much, if not more, than what he talks about in that book. So you might try A Brief History of Time if you really want to take a stab at the hard stuff. But this book, it's good to have on your coffee table, right? Because then if people come over, you bring a date back home and they see, oh wow, you have Stephen Hawking's book, and you're like, yeah, I'm pretty smart. It actually be good for your love life, maybe. Well, what's going on with these black holes in terms of this idea of Hawking radiation has to do with this kind of fun quantum mechanical effect where under very small and short time periods, the universe actually can create something from nothing, and that energy, and we've talked a little bit about this, how E equals mc squared, energy and mass are kind of the same thing, and the idea behind why stars shine like the sun is that mass is being turned into energy. 4 protons go in, 1 helium nucleus comes out, but the helium nucleus is a little bit less massive than those 4 protons. Where did that mass go? It got turned into energy, and then that's the energy that ultimately powers the sun. So in that case, that's mass going into energy. The opposite direction can also occur where you can have just a bundle of energy and you can then turn it into particles. We know that this had to have happened in the early universe, and we have actually detected these sorts of things here on Earth. It's a kind of related phenomenon called the Casimir effect, where if you put 2 plates that are separated by like a nanometer in distance, so 2 plates are essentially really, really close to one another, but there is a little bit of a gap between them. If you very carefully measure the forces that are acting on those plates, you can actually detect that there is something trying to push the 2 plates apart. And it's not the plates themselves, but that there are particles coming in and out of existence everywhere in this room, right? Everywhere that you are here, particles are constantly coming in and out of existence. And typically they form and then, a picosecond later, they turn back into energy and go away. Typically they find each other almost immediately and go away. But in the case of the Casimir effect, right, you can, in that short amount of time, and given that there's enough of them happening in between the 2 plates, you can kind of see some random fluctuations in the 2 plates that they kind of do feel like there's something kind of repelling and attracting them, so they kind of wobble as a result, and we call it the Casimir effect. And the idea here is that we think that there are virtual particles that are being created more or less from nothing, right? The pure energy is turning into particles, but then again, they usually just find themselves and turn back into energy almost immediately. So you could have a little bit of nothing, and then that might turn into a neutrino, and because you have to obey conservation laws, an antineutrino, or a proton or antiproton, or an electron or an anti-electron, or a quark or an anti-quark. And then they exist as 2 separate particles, and then they typically find each other again and cancel each other out. If you put a proton and antiproton together, they turn back into energy or turn back into photons. So we think that this is happening a lot, and we call these virtual particles, because again, they are essentially very short-lived, and you could think of them as not really ever existing as particles, because they just come and go. But then things can get interesting if you think about what could possibly be going on near a black hole. Where again, we think this sort of stuff is happening everywhere in the universe. But what if these kind of particles are coming in and out of existence near a black hole? And again, usually the idea is that you have two particles and a little bit of energy is borrowed. In this case, it's kind of borrowed from space itself. So near the black hole, you can imagine there's a severe distortion from the black hole as mass and energy just being present. And essentially, you can take a little bit of that energy from the black hole and then create kind of two virtual particles that essentially then find each other right away and disappear. And so that energy that was kind of borrowed from the black hole then gets just put back into the black hole in terms of the grand scheme of things. And if this happens inside the black hole, no difference, right? A little bit of energy is borrowed from the black hole that becomes an electron and an anti-electron, but then they find each other again, and then it cancels out. And the ultimate energy, or since E equals mc squared, the ultimate mass of the black hole does not change as a result. But then what happens when you're kind of near this event horizon? Suppose you're very close to the event horizon, and then and then a little bit of energy is borrowed from the black hole and turns into two particles. Again, this figure is using an electron and an anti-electron or positron. Again, usually they just find each other again, or they just find each other again and cancel out. But suppose you have this happening right at the edge of the event horizon. It could be that, and when they form, one of them falls into the black hole while the other one still remains outside the event horizon. In this case, it is conceivable, or at least is the idea, the basic idea behind what Hawking is talking about. It is conceivable that since these two things got separated and were unable to find themselves again, that they might actually never be able to find themselves and then cancel each other out again. So it might be possible that one falls into the black hole, where the one is free as long as it remains outside the event horizon, allowed to escape throughout the cosmos, in which case it becomes not a virtual particle, but we believe it becomes a true particle that then whizzes around the cosmos. And so ultimately, what has happened is that a little bit of energy was borrowed from the black hole to create two particles. But then one of them goes back into the black hole, so the black hole then gets one of those particles back and that gets its energy back. But then one of those particles escapes and takes away from the black hole a tiny little bit of the black hole's energy. Again, since E equals mc squared, the black hole then loses, as a result, a tiny little bit of its mass. And so ultimately, the mass of the black hole has decreased ever so slightly. And you can imagine, if you let this go on long enough, perhaps the black hole could slowly but surely evaporate away. And essentially everything inside the black hole would be returned back as all these kind of virtual particles, as protons and neutrons and quarks and whatnot, that could then be recycled back into space. So that's kind of the basic idea of black holes can evaporate. So notice again, if you throw yourself into a black hole, you're not going to get lucky and get shot out of the black hole still in one piece. You're still going to be ripped to shreds inside. You're going to be turned into mass and energy inside the black hole, but then maybe that energy then can be turned back into particles along the event horizon of a black hole. So you might then get spat out one electron at a time or something like that. The tricky thing with this is, and why this has not yet been detected, is that the rate at which you expect this to happen decreases the bigger the black hole is. So essentially for supermassive black holes, essentially this is not happening at all, or it's happening at such a slow rate that actually more stuff is falling into the black hole at a much larger rate than this evaporation might occur. So most black holes in the universe we think are currently growing as a result, just because they're gobbling up more stuff. But you could think in the theoretical limit where all the stuff in the universe has gotten used up and everything kind of turns into white dwarfs and neutron stars and black holes or whatever, and nothing new is falling into these black holes, that maybe theoretically they could slowly but surely start to evaporate away. And this speeds up the more and more you go, right? So the smaller the black hole gets, you can calculate how frequently you expect this to occur. And actually it accelerates the smaller it gets, right? So as the black hole got smaller and smaller and smaller, the rate at which it was spewing back out mass should theoretically increase. In which case, if you have like a tiny black hole, miniature black hole, it's possible that they would kind of just burst and entirely disappear. We thought maybe when CERN in Switzerland was turning on its particle accelerator for the first time, and you might remember this, they talked about how there might be a risk that we could create tiny, tiny, tiny little black holes, and people were scared that the Earth would get gobbled up. Of course, they didn't understand that outside the event horizon, that's okay. Those tiny little black holes actually would have been perfect candidates for this, to observe this kind of Hawking radiation. And Stephen Hawking, before he passed away, actually was hoping that maybe we'd be able to see, these tiny little black holes form, but then immediately burst away if Hawking radiation actually was correct. Fortunately, we didn't see the creation of any of these kinds of black holes, let alone any sort of development of kind of evidence of this sort of Hawking radiation. But that doesn't mean it's not happening. Could be that those experiments weren't set up to actually make black holes. What I think is more likely the case is that we don't fully understand the physics of what goes on when you try to have very, very massive gravitational things, along with it being very, very small, which you then have to incorporate quantum mechanics and general relativity together. And actually, that's a big open-ended question in astrophysics today, really in all of physics, is that kind of the two main pillars of physics is general relativity and quantum mechanics. But it's very obvious when you try to do simple calculations with them together that there's a mistake somewhere, or not necessarily a mistake, but that it's an incomplete theory. Because when you try to do calculations that require both, you get clearly nonsense. So that's the whole idea behind things like string theory or M theory and things you might have heard of, where the idea is there's clearly general relativity and quantum mechanics are not the end all in our understanding of the universe. Maybe we'll find that relativity is wrong on these scales, or quantum mechanics is wrong on these scales. So something has to happen, but it would have been kind of cool if we would have seen these sorts of things. And it is going to be very hard for us to ever see this in reality. Again, for black holes that are like the mass of our sun, you can estimate that it would take probably about 10 to the 60 years for one of those things to evaporate. And for comparison, our universe is 14 billion years old, or about 10 to the 10 seconds old. It would take 10 to the 60 years, or about 10 to the 67 or so seconds for a regular black hole to evaporate. For supermassive black holes, like in the center of our galaxy, about 10 to the 100 years. So those things are not going anywhere anytime soon. There's a very, very slight effect, but again, it's kind of an attempt to merge ideas of quantum physics and relativity. So if we can or cannot detect it, it actually might say something about what physics is like on these sorts of scales, where you have something so massive like a black hole, but it's on such tiny, tiny scales that you have to deal with quantum physics. So TBD, I would say, in the case of Hawking radiation and that sort of stuff. I think we need to improve our understanding of this sort of physics before we can move forward there. All right, there is my optional lecture. Usually this is this material is spread across 2 lectures in class. But again, since I lost that one lecture, I figured I would do this as a video instead. All right, see y'all later.